Fantastic, we profile the amazing, jaw-dropping scientific discoveries which are revolutionizing our world and touching our lives. And with us today is an astronomer who'll talk to us about our own backyard. What's out there in the night sky? You look at the night sky, you see billions upon billions of stars, but what is out there? Well, believe it or not, what we think is Earth-like planets are out there, perhaps twins of the Earth, doppelgangers of the planet Earth. Billions of them in outer space. And with us today is Dr. Michael Summers, professor of physics and astronomy at George Mason University, talking about his new book, Exoplanets. You know, when you see movies like Star Wars and you see things like double star systems with planets going around them, most astronomers say, bah, humbug, that's just Hollywood hype. You can't have planets going around double stars. Well, boy, were we wrong. Realize now that we have identified not just planets going around a double star, but a triple star system. Think about that. Planets that were once unimaginable, we now see with our telescopes and our instruments in outer space. They're called exoplanets, and we've identified more than 3,000 of them just within the last decade or so. And we believe that perhaps on average, every star in the Milky Way galaxy has planets and a solar system going around them. So this is incredible. It's an existential shock looking at the night sky, realizing that perhaps somebody is looking back at you from outer space. And then, of course, we'll ask Dr. Summers the question of all questions, and that is, if there are so many planets out there, if there are so many Earth-like planets that have perhaps liquid oceans like ours, then how come they don't visit us? I mean, it's lonely being here on the planet Earth with no one to talk to other than other Homo sapiens. Are there aliens like what we see in the Hollywood movies? Well, we'll ask him that question. But in the meantime, we'll talk about some of the most bizarre planets that we've discovered. Planets made totally out of water. Planets made out of diamonds. That's right, a diamond planet. Planets going around a dead solar system, and these planets shouldn't even exist according to modern physics, but there they are, visible through our instruments. And one day we'll have pictures. One day we'll have pictures of the surface of these planets. And some of them are just a hop, skip, and a jump from us. The closest star to the Earth is Proxima Centauri, and sure enough, there is an Earth-like planet going around Proxima Centauri. A hop, skip, and a jump from the planet at 4 light years. In fact, my colleague Stephen Hawking has made a proposal to create the first starship to visit Proxima Centauri b. It's not going to look like the Enterprise. It's basically a postage stamp with the power of a chip with a parachute inflated by a laser beam of 800 gigawatts of power, and that will reach the nearby stars, perhaps in 20 years. Okay, well, once again, this is Science Fantastic. After the break, we're going to bring on Professor Michael Summers, author of the book Exoplanets, and we're talking about what's out there in the night sky. When you look at the night sky tonight, realize that somebody could be looking back at you from outer space. And we have an encyclopedia now, an encyclopedia of thousands of planets orbiting other star systems. And it really makes you wonder, are we alone in the universe? Welcome back to Science Fantastic with Professor Michio Kaku. Once again on Science Fantastic, we're going to bring on an astronomer who will talk to us about some of the most bizarre, some of the strangest things we see out there in outer space. Our special guest today is Professor Michael Summers, co-author with James Treffill. The book is called Exoplanets: Diamond World, Super Earth, Pulsar Planets, and the New Search for Life Beyond Our Solar System. And we should also point out that he's a professor of physics and astronomy at George Mason University. Since 1989, he has been involved with several NASA missions, including the New Horizons missions to Pluto, And we should point out that his co-author is James Treffield, professor of physics also at George Mason University. So, Professor Summers, glad you could be on Science Fantastic.
It's a pleasure to be here and chat with you.
Great. Well, the first question we always ask our guests is, how did you as a youth, think back when you were 10 or so, how did you as a youth first get interested in science?
Well, actually, that goes back to when I was about 6.
Mm-hmm.
My father bought me a very, very small telescope, probably about what you could buy now for $30. And I had the incredible fortune of growing up in Kentucky, where the skies are very, very dark at night. But I had no idea what I was doing, so I took the telescope out back in our backyard, and I just looked around at some bright stars. And it just so happened the very first object I looked at, a bright yellow star, turned out to be Saturn. And now it was tiny, but it was a very crisp image, and I could see the rings.
You could see the rings, huh?
I
Amazing.
could see the rings. They were not clear, they were not individualized, but they were clearly rings. It was something that was just so foreign to me that I had to check it out. And then did a little bit of library work. I learned about Saturn, how big it was, and to realize it's about 90 times the mass of the Earth was just astonishing to me. And then to realize that it has a ring system that would span from the Earth to the Moon, which is even more astonishing. And then I tried to figure out what the rings were made of, and it seemed at the time nobody knew, which was even more weird. And I think that just kept me interested in planets from that period on. I mean, I had other interests as time went on, but even when I was studying physics, I wanted to gravitate towards astronomy and find out what planets were like and what atmospheres were like. But of course, then we only had 9 planets. Now we have thousands. So the world has changed quite a bit.
And of the 9 planets, Pluto got kicked out of the solar system, right? I mean, it's no longer a planet. It's in the solar system, but it's no longer a planet.
According to the IAU definition, Pluto is not classified as a planet. But I think there's general agreement that definition is somewhat flawed. I mean, if you took the Earth and put it where Pluto is, then the Earth would no longer be a planet. So that's controversial, and I suspect that issue is not settled just yet.
Okay, well, let's just jump right into your book, Exoplanets. When I was a kid growing up, we learned that our solar system is perhaps normal, that other solar systems in the universe are probably going to look just like us with rocky planets toward the center of the solar system, circular orbits with gas giants much further out, also in circular orbits. But boy, were we wrong, right?
Right. Yeah, we were wrong on many fronts, and that's, to me, that's the most exciting thing about studying exoplanets, is that it's just everywhere we look, every discovery we make, every time we have a new telescope, that we can peer deeper or in more detail around other stars, we get surprises. And one of the first surprises was that there were giant planets that were very close to the central star. And there was a little bit of an observational bias because that was about all the kind of planets that we could detect at the time. But it seemed like we had gas giant planets close to stars, and we called those hot Jupiters, even though we didn't understand how you could get them that close, how they could form that close. But it was completely different than the solar system that we're in. And so that was a bit of a mystery at the time. And then we found planets around pulsars, which was pretty wild. A pulsar is the cinder of a supernova that explodes, and the explosion, we think, should vaporize any planets around the supernova. But yet we found, more than one example of planets around pulsars, and then it just gets wilder as you go on. There are planets that appear to be made out of things like water. I mean, pretty much all water. Now, we could be wrong on the mass and the size of some of these things a little bit, but still, you're talking about a fair fraction of the planet being water, maybe half water, or maybe even more. So they would be classified as water worlds, and that's pretty wild. And then there's some suggestion that one planet may be even mostly carbon. And, of course, all of us know what carbon is at high pressure, so that would be crystalline diamond. But that gets kind of wild if you think about that world. It's about 5 times as massive as the Earth. So in the core of it, the pressure would be about 100 million times sea level pressure. in our atmosphere, and the diamond would then flow as a liquid. So that's pretty wild. That's so far away from our normal experience that it's hard to even visualize something like that.
Okay, well, let's
So,
take them.
yeah.
Let's take them one at a time.
Okay,
First of
sure.
all, you mentioned that these hot Jupiters were discovered. We once thought that the Jupiters should be way, way out there, like Jupiter and Saturn, away from the sun. Does
Yeah.
that mean, therefore, that these Jupiters have wandered, that they were formed far out and then wandered close to the sun? If so, then any Earth-like planet would have been destroyed in that process, right? Could you elaborate on wandering Jupiters?
Yeah. I think that's the consensus now, is that they did form far out beyond what we call the ice line. There's a distance from a forming star beyond which you can condense not just rocks and metals, but ice onto protoplanets that aggregate and coagulate and form planets. And that's how you get giant planets out there. You can aggregate ices like water and carbon dioxide and methane and even hydrogen gas, and all of that can accrete to form a large planet. But that has to be very far out. In our solar system, that would be further out than the orbit of Mars. And so you've got to get those somehow inward towards the sun. Now, how they migrate, how they wander, I think I like the word migrate is a little bit better because it's probably a steady type process. How they wander and migrate into the inner part of the stellar system is not completely worked out just yet. It could be some sort of frictional drag or electromagnetic interaction with the magnetic fields of the central star. But yeah, you're absolutely right. If there are rocky planets that form closer, and you've got a giant planet that's migrating inwards, then the rocky planet's going to be in trouble. Most likely, it will be ejected from the system or into a much longer orbit or outside of the orbit of the gas giant, or perhaps ejected completely from the forming star system entirely. But yeah, that's a problem for rocky worlds that form close if this kind of migration does occur generally.
So thank goodness our Jupiter does not migrate.
Right.
Otherwise, this conversation would be in deep space right now.
Yep.
Now, as I understand the orbits of these gas giants, we thought would be circular, like in our solar system. They are more or less circular, but some of them are highly elliptical. Now, does that also mean that any Earth-like planet would be flung into outer space because Jupiter simply got too close to the Earth-like planet?
I suspect that it means several things, the most important of which is that close gravitational interactions between planets are probably very, very common. We know in our solar system that collisions early in solar system history between planets were common. Like Mercury suffered a collision with another planet that stripped off its crust. The Earth had a collision with a Mars-sized planet that formed our moon. And Uranus had a collision that tipped it over on its side, and Pluto had a collision that formed its large moon Charon, and the four small moons. So collisions are common, and a collision can destroy both objects, form a new one, or they can be close just to change the orbits of the two objects. It can sling an object completely out of the stellar system, and getting an eccentric orbit then can be a consequence of several things: a close encounter, or perhaps even multiple encounters between a gas giant and other gas giants and other planets. It's hard to work backwards looking at just an elliptical orbit to know exactly how it got that way. There are multiple paths that might lead to that.
Well, you mentioned that the moon was probably blown out of the Earth billions of years ago. However, look at the planet Venus. Venus goes around the sun in the same direction as the Earth, but on its axis, it spins backwards.
Yeah.
Therefore, the question is, why does Venus spin backwards? Maybe it was also suffered a gigantic collision. What are your thoughts?
Well, I don't know of any evidence that it suffered a collision, but there are other types of interactions between planets besides direct, physical contact. And one of those is long-distance gravitational tugs. We call them gravitational tides. Like the simplest example I know of is that the Earth and the Moon are gravitationally locked into a resonance. That is, the the moon rotates on its axis every time it goes around the Earth once. As a consequence, it always shows the same face to the Earth. We only see the same face of the moon from the Earth. We'd never seen the other side of it until the space age, when we could have spacecraft to go on the other side of the moon and send us pictures back. In the same way, there could be longer distance gravitational, these tidal type interactions between planets. And I suspect that the rotation rate of Venus is more a consequence of that tidal interaction between the Earth and Mercury than it's due to a collision. But here we don't really have enough information to work backwards and see what or to speculate with any confidence what happened early in solar system history. With the Earth, we have the moon. So we've got a clear, obvious mystery to explain, and the collision seems to explain it nicely.
Okay.
Venus, we don't have a moon in orbit about it. In fact, the lack of moons probably is telling us something about the evolution of Venus. I'm not exactly sure what, but it's probably an important clue.
Okay, now let's leave the world of gas giants, and now let's go to exoplanets that resemble the Earth. Just a few months ago, there was the astounding announcement by NASA scientists that there's a solar system with seven Earth-like planets going around it. Could you elaborate?
Yeah, that's the TRAPPIST-1 star, and it has a system of 7 planets that are much like the Earth. When I say much like, we think that they're probably made up of rocks and metals, a lot like the Earth, and their size seems to be, in the size range of terrestrial planets like the Earth and Venus. Maybe 2 of them are a little bit smaller and the others are a little bit larger. But that system is intriguing for many reasons. One is that there are 7 Earth-like planets, 3 of which are in the right range of distances from the central star so that you could have liquid water stable on the surface. And we call those planets in the habitable zone, or sometimes called the Goldilocks zone. Now, that doesn't mean that you can't have water on all of them. In fact, probably all of them do have water. But those 3 could have stable liquid water on them, and that's what we consider a requirement for life as we know it. So it's intriguing because of that. But just to get 7 planets, Earth-like planets, around a star is pretty astonishing. I mean, we just have 2 in our solar system, or 3 if you include Mars, but 7 is pretty interesting. And then if you think about the central star is an M-dwarf star, which is a very, very common type of star in our galaxy. We didn't know if planets could form around these stars. They're smaller than the sun and a lot less massive. But now we know that they can. So that means that the 40% of all the stars in our galaxy that are these kind of M-dwarfs may have planets. And so that's pretty exciting. There may be lots of these systems out there that are interesting. And another thing that's kind of nice about the TRAPPIST-1 system is that it's only 40 light years from the Earth. Now, that means that with future telescopes that we're going to have, like the James Webb Space Telescope, it's close enough that we'll be able to probe the characteristics of the surfaces of these planets.
Okay, Michael, we have to take a short commercial break.
Sure.
But after the break, we're going to continue a discussion of exoplanets with Dr. Michael Summers and his co-author, James Trefil. Welcome back to Science Fantastic with Professor Michio Kaku. In this hour, we're talking about our backyard, the Milky Way galaxy. How many stars out there have Earth-like planets going around them? What does that mean for the search for intelligent life in the universe? We've seen all the Hollywood movies and all the Hollywood hype. Let's not talk about the science of what's out there. Our special guest today, once again, is Professor Michael Summers, a professor of physics Physics and Astronomy at George Mason University. And since 1989, he's been involved with various NASA missions. His co-author is Professor James Trefil, also at George Mason University, and the book is called Exoplanets. Well, Michael, where we last left off, we were talking about a system with 7 Earth-like planets going around it. But some people say, well, what about the closest? The closest planet to our sun, other than within our solar system, and we now know that it could be Earth-like, Proxima Centauri b. So tell us a little bit about what's out there, maybe 4 light years from the planet Earth.
Yeah, as you say, just 4 light years is really close from galactic standards. It's close enough that within 20, 30 years, we could even have images of its surface. The technology is advancing fast enough we'll be able to do that. But this planet is not just your average exoplanet. It appears to be very Earth-like, and it's also in the what we call the habitable zone around Proxima Centauri. So it's Earth-like. It may have water on the surface. We don't know the temperature of the surface accurately yet. The water might be ice or it might be liquid. We just don't know. We will in a few years. But because it's so close, the future telescopes like the James Webb will be able to determine the composition of the atmosphere. And that's going to open up a sort of a new level of inquiry into these objects, because all of us are interested in life on other planets. And to determine if there's life there, you have to look at signatures of that life. And those signatures are most often called biomarkers, or markers or signatures of biology. And these kind of biomarkers that we're looking for are chemical byproducts of their metabolism that we find in the atmospheres. Like on the Earth, we're breathing oxygen, which comes from photosynthesis, and there's methane in the atmosphere that comes from methanogenetic bacteria. On other planets, if we see oxygen and methane and maybe ozone, that's going to be a pretty good signature that there's something like life going on. So that's what we're excited about with the nearby Earth-like exoplanets, is that we'll get the technology to probe them carefully enough to determine whether there's signatures of biology of life as we know it. Of course, that's a very parochial view. There may be all sorts of life that we don't understand or we don't know, but life as we know it is something that we know enough about to look for.
Okay, now let's take a census of the Milky Way galaxy. Our galaxy has roughly 100 billion stars, and when we look at stars in the heavens, what fraction of them have planets going around them, even Jupiter-sized planets? So of the stars you see at night, what fraction would you estimate have planets going around them?
Yeah, that's really intriguing. I've spent a lot of time looking up at the sky, especially when I was younger. You know, the statistics right now really only give us a lower limit. There may be many more planets that we haven't detected yet that may improve our statistics. But right now, I would estimate that probably every star, on average,
Every star
on average has one Earth-like planet, on average.
Earth-like planet?
Yeah.
Really?
There'll be some, like the TRAPPIST-1 system, that have 7, and there will be some that have none. But on average, I'd say every star probably has one Earth-like planet, probably 10 or so planets if you include everything from Pluto size up to Jupiter size.
Okay, Michael, we have to take yet another short commercial break. But after the break, we're going to talk about a census of the Milky Way galaxy and what fraction of them may have intelligent life forms on them. Welcome back to Science Fantastic with Professor Michio Kaku. In this hour, we're talking about the universe. That's right, your backyard, the Milky Way galaxy. With us today is Professor Michael Summers of George Mason University, author of the book Exoplanets, with co-author Professor James Trefil. Well, where we last left off, we were talking about a census of the Milky Way galaxy. So, Professor, when you look at the night sky tonight, and you look at the average star out there, you're saying that on average, there is one Earth-like planet per star you see at night. That is incredible, right?
That is just jaw-dropping, incredible. I don't know how else to say it. That means that in our galaxy alone, there are more Earth-like planets than the number of people that have ever lived on this planet. That's just, it's hard to find words to describe something like that. And the number of total planets is at least 10 times that much. And that's only the planets that we can extrapolate that are bound, that are gravitationally tied or tethered to central stars. There are probably a huge population of planets that have been flung out into the interstellar medium, which we call rogue planets, that may even outnumber the gravitationally bound planets. So planets are everywhere. I tell my students I've got job security now because there are more planets known than planetary scientists in the world. But that ratio is going up enormously. There are 3,600 planets now confirmed. We're discovering whole new worlds at a rate of about 2 per day. And that's going to continue. In 10 years, we'll know of 100,000 planets around other stars. They're just everywhere. And Earth-like planets seem to be common. I just find that so astonishing. I don't even know how to talk about it.
Okay, well, then the next big question is, well, what about intelligent life on them? There's something called the Drake equation, which tried to give us a rough ballpark estimate of how many of these planets would have intelligent life forms on them. How has that equation held up? And what's the, well, not exactly the consensus, but what's the feeling among astronomers as we look at the staggering number of Earth-like planets out there? How many of them may have intelligent life on them? What are your thoughts?
Well, that's something we really don't know. We just don't know enough about the factors of the Drake equation to estimate how many have intelligent life. What we can say that over the past few decades, a few of the factors, like the number of stars that have planets and the number of habitable planets around a star on average, we know those numbers pretty well. The things we don't know are like, on what fraction of those planets does life actually originate? And that's an important factor. We don't know that yet. Then once you get simple life, like bacteria, how does that evolve to intelligent life, and what are the factors involved? We don't know that component of the Drake equation either. So I think that we still are in sort of the discovery phase of fleshing out the different terms in the Drake equation. We can say that habitable planets are common, and they're probably even more common than what our statistics now give us. But that's not the same thing as saying that they are inhabited. That's something we just simply don't know right now. That's why we're looking so hard to look for biomarkers or signatures of complexity, signatures of life on other planets. We just don't know. And that's, in a way that's frustrating, but in a way it's exciting. We may be the generation that answers that question. And so it's a pretty exciting time to be alive.
Okay, now you've seen evidence of planets that even science fiction writers were not imaginative enough to come up with. For example, planets going around triple star systems. Who would have thought you could have a planet going around 3 stars? Well, after the commercial break, I'm going to ask you, what's the weirdest, some of the weirdest planets? You mentioned the Diamond Planet. We can talk about that. What are some of the other weird stuff that you've seen out there? Because we now realize that there's no such thing as an average planet. Stay tuned as we talk about what's out there in our own backyard. Welcome back to Science Fantastic with Professor Michio Kaku. There's nothing more fantastic than what's in our own backyard, the Milky Way galaxy. And did you know that scientists have been able to identify thousands of Earth-like planets out there? In fact, we think that perhaps all the stars in the heavens on average may have an Earth-like planet. Once again, with us today is Professor Michael Summers of George Mason University. Professor Summers, you've had a chance to look at this encyclopedia of planets. What are some of the weirdest ones that you've seen out there, including the Diamond Planet that you mentioned earlier?
Yeah, that's a really good question. What is the weirdest? What is the most non-Earth-like? Well, the diamond planet is certainly up there. I'm actually more fascinated with the water world. I mean, you think about it, water through and through, from the surface down to the core. Would it be uniform? I suspect that it would be layered like an onion, and the layers would represent phase changes in the water. So you could have multiple layers inside of that world. But then you've got some planets that are flung in the interstellar medium. We call those rogue worlds or rogue planets. I find those pretty fascinating too. They've been neglected a fair amount because we don't have very many detections, really only 2 detections. But you know, if you fling a planet into the interstellar medium, your first sense is to think that it's just cold and dead. But that's not true for many planets and their moons. Like if you took Jupiter and its moons and flung them into the interstellar medium, pretty much nothing would change for those because Jupiter has its own energy source and the moons are heated from tidal interactions with Jupiter. So you could have planets out in the interstellar medium that are just as habitable as they are around stars. And that's incredible because if there are more, and this is an indication that's very tentative, but there's a suggestion that there are far more of these rogue planets than there are planets circling stars. And that fraction, there may be as many as 100 or 1,000 times more rogue planets than there are bound planets. So when you think about going to the nearest star to find a planet like Proxima Centauri B, to go there, you may pass a half a dozen other rogue planets on the way. They may be hard to detect because they're not going to have sunlight to reflect, but they may be there. If this scenario, if this is kind of an accurate representation of the way the galaxy is, then that would completely change our ideas about interstellar travel. You wouldn't go to the nearest bright star. You would just have a spaceship that goes to the next rogue world, fuel up, hang around a bit, maybe create your own fusion stars, and then go to the next rogue world. And then you would eventually propagate through the galaxy. But we don't know yet. I mean, that's just a suggestion. But rogue worlds I find really intriguing because it takes a long time for them to cool off, and they could remain habitable for many billions of years.
Now, you mentioned that Jupiter, if it was flung into outer space, well, its moons may have life on them, given the fact that Europa and Enceladus, a moon of Saturn, seem to have liquid oceans underneath the ice cover. However, there's no life on Jupiter itself, right? So you're not talking about life on Jupiter. You're talking about life on the moons of Jupiter, right?
For Jupiter, life as we know it is probably not in the cards. But if you look at Jupiter's 4 large moons, Io, Europa, Ganymede, and Callisto, 3 of those moons have subsurface liquid water oceans. Europa, Ganymede, and Callisto each have oceans that in volume are larger than all the water on Earth. I mean, think about that. The moon Europa has more liquid water inside of it than all the oceans on the Earth. And Ganymede and Callisto each are the same way. Titan, a moon of Saturn, it probably has a subsurface liquid water ocean. Enceladus is smaller, but we know it has a subsurface ocean that's hot because it's spewing geysers of hot water, salty water, into space. So think about that. 5 planets in our solar system, 5 planetary bodies that have subsurface oceans of liquid water. So if these were flung in the interstellar medium along with their primary planet that they orbit, not much would change. They would still be habitable from the perspective of having liquid water and energy and raw materials. So, the idea of rogue planets being habitable, being havens for life, I think is very plausible. It's something that's really fun to think about in any case.
Okay, now earlier you mentioned the diamond planet. Could you elaborate once again for those people who just tuned in? What is a diamond planet?
Well, when we discover planets, the first bits of information we get typically are the mass and the size of the planet. And from those 2 numbers, you can work out the density, how much, say, kilograms per cubic meter on average is inside the planet. And when we do that for a couple of planets, like 55 Canopy E, you find that the density is consistent with elemental carbon. And that's kind of astonishing because the density of the planets in our solar system are not at all like that. Now, that doesn't mean that we've discovered carbon there, but it means that the most likely explanation for that planet is that the bulk of it is carbon. And so if you have a planetary-sized body made up of elemental carbon, it's going to be under high pressure, and so it will most likely be in the form of crystalline diamond. It'd be a fun place to think about, because in the interior, the diamond could be under such high pressure that it flows as a liquid, and you could even have liquid spurts of diamond onto the surface as diamond volcanoes, which the diamond then crystallizes, and you would have chunks of diamond that fall on the surface. Now, the surface
Okay.
doesn't look.
Okay. We have to wind up. One last quick question, 15-second answer. Why don't the aliens visit us? Are we not interesting, or are they perhaps bored with us? How come the aliens don't visit us? 15-second answer.
Okay, my gut feeling is that they probably already know about us, but we're too dumb to detect them.
Okay.
But I don't think they're going to come here and steal our water or our women. I think we don't have much that would be of interest to them, except our own culture. That might interest them.
Okay, our time is up. Once again, our special guest today has been Dr. Michael Summers, and the book is called Exoplanets. And you've been listening to Science Fantastic with Professor Michio Kaku.
This is Science Fantastic. Science Fantastic with Professor Michio Kaku.
This is Science Fantastic with Professor Michio Kaku. On Science Fantastic, we profile the amazing, jaw-dropping scientific discoveries which are revolutionizing our world and touching our lives. And once again, in this hour is open mic. We're going to throw the lines open because this hour is your hour. This is the time when you can get to the telephones and give us a call. Let's say you're watching the TV and there's some kind of story about cancer research, some kind of story about disease, some kind of story about Mars, and you're left there just staring at the TV set all by yourself. There's nobody to talk to. Well, you can talk to me. Give me a call. You'll get a recording. All we ask of you is that you leave your name, call letters of the radio station you're listening to, and the city you're calling from, and perhaps you can get on Science Fantastic. And some people say, well, my questions are kind of dumb, and I don't want people to laugh at me, and so on and so forth. Well, no one's going to laugh at you, because sometimes the dumbest questions are the deepest questions of all. For example, once upon a time, there was a 23-year-old gentleman who asked a simple question. Does the moon fall? A simple question. Does the moon fall like an apple? And the astounding thing was he solved the problem. Yes, the moon does fall. It falls just like an apple. It doesn't hit the earth because, of course, the earth is round and the moon goes around the earth. But yes, the mathematics of a falling apple are the same as the falling moon. In fact, everything is falling. Everything is in free fall. When you walk, you're actually falling and hopping, falling and hopping. Everything's in free fall. Well, that 23-year-old gentleman was Isaac Newton. And to solve the problem, he had to invent a new mathematics called calculus. In other words, Math 1 in any college campus. So sometimes the dumbest questions are the most profound of all. And a 16-year-old boy asked a simple question, and that is, can you outrace a light beam? It took 10 years for that 16-year-old boy to finally crack that problem, and that young boy was called Albert Einstein. And when he solved the problem, he realized that no, you cannot catch up to a light beam because light always travels at the fastest velocity in the universe. And that led to the atomic bomb. It unlocked the secret of the stars and gave us the modern age. So sometimes the dumbest questions are the most profound of all. Okay, well, let's move right along now and take the first listener phone call.
Hey, Professor. My name is Jeremy from Battleground, Washington. I listen to you on trn1.com, and I've been reading lately some books by Robert Schoch and Graham Hancock about the theory that civilization may be a lot older than we before thought. And I was wondering, with the find of Göbekli Tepe in Turkey, if you have any comment on that or how you feel about that.
Well, yes and no. It turns out that every year archaeologists discover more and more about the ancient civilizations of the past, and we realize that a lot of our time frames have to be readjusted to compensate for that. For example, many of the things mentioned in the Bible, things mentioned in German mythology, like, for example, the Trojan Wars and the city of Troy, turned out to be true. We actually found the city of Troy. And, however, you can put some boundaries on this, and that is the Ice Age. The Ice Age ended roughly 10,000 years ago. And before then, it was quite difficult to have what is called modern civilization. We were basically nomads. We were chasing after the deer and the buffalo, and if the deer and the buffalo left and left you behind, you starved to death. So you had to chase after the deer. You were migrants. You were permanently on the road because your food was also on the road as well. Therefore, cities as we know them were not possible. There were isolated settlements, of course, but you had to have a source of food. Then, after the Ice Age ended, then the age of agriculture started, and then you could have the first stationary villages. Even if the buffalo and even if the deer left, you didn't starve to death because you could plant apple seeds and harvest them in your own backyard. And with the discovery of agriculture came the first villages, then the first cities, then the first empires began to rise out of the desert and the jungle. So when we look at ancient civilizations, recorded history goes back roughly 5,000 years. Beyond that, things get very, very fuzzy. But yeah, many of the things mentioned in the Bible, you can begin the process of dating some of these things. And you realize that, yes, you can date history going back, recorded history going back 5,000 years. Now, beyond that, things start to get very fuzzy because, of course, writing was not invented back in those days. And so is it possible that there could have been new civilizations between, let's say, 5,000 to 10,000 years ago that haven't yet been discovered? And the answer is, well, yes. Because as long as there was a food supply for these people, like agriculture, it meant you could have stationary cities without having to chase after the deer and the buffalo like a bunch of nomads. But beyond 10,000 years, well, North America was under a half a mile of ice. And so it was quite difficult to create a sustaining civilization when your food basically left, and if it left without you, you starved to death. Okay, well, let's move right along to the next listener phone call.
Hi, Dr. Kaku. This is Carlos. I'm listening in L.A. on TalkRadioNetwork.com. I wanted to ask, I was watching this old TV show called Revolution, and the basic premise is the planet loses the ability to create electricity. So I wanted to see if that was even possible. Seems a little far-fetched to me, but what do you think? Thanks.
Well, you mentioned something very important. We take electricity for granted, but if you look at history going back, we've had three great revolutions in science. The first was the steam engine, and the steam engine made possible the Industrial Revolution and factories and created the modern industrial working class. The second great revolution was the electric revolution that you mentioned. They gave us radio, television, automobiles. It gave us many of the wonders of the modern electric age. Then the third great revolution is the high-tech revolution with lasers and computers. A fourth wave is also coming. The fourth wave is artificial intelligence, biotechnology, and especially nanotechnology. Now, you mentioned what happens if, one of these revolutions is stymied or caught right in the middle. Well, the electric revolution depends upon our ability to harness the power of electrons, and there are ways in which you can conceive of where electricity may not be possible. For example, if the air becomes very humid, electricity does not work well under certain different atmospheric conditions. So yes, it is possible you can conceive of certain scenarios where electricity is not possible. But then some of these scenarios are so severe that people would not be possible as well. So the premise of the TV show is that somehow you could simply turn off electricity and still keep humans breathing and operating normally in our atmosphere. Now, this, of course, affects perhaps life in outer space. Some scientists think that if life in outer space existed, well, they must be able to harness electricity and computers to build rocket ships. But that means their atmosphere has to be similar to our atmosphere, which can sustain lightning bolts without short-circuiting things. For example, if you have a water world out there that is an aquatic species, you might be able to have intelligence up to a point. So if you have fish-like or octopus-like creatures in outer space, yes, they would be able to invent machines. But then when it comes to, for example, the steam engine, they would have a problem because a steam engine requires oxidation. It requires fire. And in an aquatic world, you cannot light a match. Then electricity would be short-circuited because electricity goes right through water. And so those are two revolutions which may not exist in a water world in outer space. So we are fortunate enough to be on a planet where it is possible to have fire, that is oxidation. It is possible to have an industrial revolution and the electric revolution because our atmosphere will support electricity without short-circuiting them. So to answer your question, well, yes, it is possible to create a world without electricity, but that world probably wouldn't have humans either. So to have humans, like in a Hollywood movie, and have no electricity is quite difficult. But yes, we scientists have looked at that because in outer space there could be civilizations that do not have electricity, and their progress would be stunted as a consequence. Welcome back to Science Fantastic with Professor Michio Kaku. Once again, you're listening to Science Fantastic, a program which profiles some of the most amazing developments in science. Okay, moving right along, let's take the next listener phone call.
Hi, my name's Ryan from Spokane. My question is, how many people would go to the Mars base once it's constructed?
Well, you ask a very practical question that billionaires are asking now, specifically Elon Musk, the billionaire behind Tesla, PayPal, and SpaceX, and also Jeff Bezos, the brains behind Amazon and Blue Origins. Well, first of all, yes, people are taking volunteers for real. Elon Musk, pioneer of SpaceX, will launch the first unmanned probe to the moon in many a decade, starting later this year, if all goes well. And next year, he wants to send 2 volunteers circling around the moon in the first manned mission to the moon in 40 years. The cost? Well, yes, you can be one of these 2 volunteers to go around the moon for a paltry sum of $80 million. So if you are a fellow billionaire, yes, you too can join Elon Musk and explore the universe. $80 million to be one of the first people to go back to the moon. Then what about Mars? Well, you have to be careful now because there are some, shady, bogus operations that claim that one day they'll create the first settlements on Mars in a few years. There's a program called Mars One, and it has enlisted many volunteers to be part of the first mission to Mars. There's a problem, a big problem, and that is money. It has no major benefactors. So if you sign up for Mars One, you're not going to go to Mars anytime soon. And that's my personal opinion. But yes, already they have many people volunteering for a one-way mission to Mars. Now, personally, I think we should offer a 2-way mission to Mars so they can come back and talk about it. And that, again, is where Elon Musk comes in. 2024. That is the time when we may have the first manned mission to Mars. And yes, probably you can buy a seat on that. Just go to SpaceX's website and perhaps there's a place where you can begin the process of signing up. However, I should also point out some of the politics involved. President Donald Trump has now weighed in because of the fact that if we have the first manned mission back to the moon by 2020, let's say, that would be quite a feather in the cap of President Donald Trump. So Donald Trump has actually asked NASA for an accelerated time frame. NASA's time frame is much slower than Elon Musk's time frame. NASA has the SLS booster rocket and Orion space module. Their first unmanned mission to the moon would be around 2020, and perhaps a manned mission to the moon sometime in the 2030s. Well, President Donald Trump has asked NASA, can you accelerate that so that by the end of President Trump's first term, that is 2020, we would have a manned mission that goes around the moon, and then 2024, at the end of a hypothetical second Trump term, there would be the first manned mission all the way to Mars. So to answer the question, right now we do not have an official list of volunteers to go on SpaceX's mission to Mars by 2024. But hey, go to the website and maybe one day we'll see a column whereby you can sign up. But watch out for, well, shady operations that promise you a seat on Mars, but in reality, I don't think they're the way to go. Right now, we have 3 serious proposals to go into outer space. One, of course, is NASA with the SLS booster rocket. Some people criticize their time frame for being too slow. That's why the president has asked for an accelerated program. Then we have Elon Musk with the Falcon Heavy booster rocket. And they've already made history by reducing the cost of space travel rather dramatically. And then we have Jeff Bezos of Amazon. He wants to create a moon base first, perhaps a colony of astronauts that will be part of a permanent presence on the moon, and after that, on to Mars. In other words, we may have a traffic jam around Mars. Who knows for sure? But we have not 1, not 2, but 3 proposals to go to Mars. Okay, well, let's move right along and take the next listener phone call.
Hi, Professor. This is Josh. What do you think about the double slit experiment?
Wow. Well, you are asking one of the big questions in all of physics and philosophy, and that is the reasoning behind the double slit experiment. Well, let me explain. If I have a sheet of paper and punch a hole in it, and then shoot a bunch of electrons at that hole, and then you ask yourself what comes out the other end, most people would say, well, the answer is obvious. You'd have a steady stream of particles called electrons that come out the other end, because electrons are made out of particles, right? Well, that's a naive answer. When you actually do the experiment with 1 or 2 holes, it turns out that at the other end, you do not get an image of just 1 hole or 2 holes. What you do is you get a wave-like pattern, an interference pattern. In other words, the electron has wave-like properties, and it's not simply a dot. It's not simply a particle. Somehow it also has wave-like properties. Now, the double-slit experiment is bizarre, because in order to have an interference pattern from 2 slits, you have to have waves from 2 slits interfere with each other. 2 waves from the top hole and the bottom hole interfering with each other. Now, here is the killer. Shoot 1 electron, not 2, 1 electron at 2 holes, and look at what you see at the other end. If you do this repeatedly, you get a pattern of dots on the other side. And the pattern of dots, once you shoot millions of particles through the double holes, what do you get? You get a wave-like pattern as if the electron went through both holes. Now at this point, your brain starts to explode, because I said that the electron is a particle and it goes through 2 holes, leaving a pattern that is a pattern of a wave that went through 2 holes. In other words, the electron is 2 places at the same time. How can that be? Your brain goes berserk thinking about this, and after the break, I'll answer the question. How can one electron go through two holes simultaneously? How can you be two places at the same time? This is not an academic question because our computer revolution and laser revolution depends upon this answer. Welcome back to Science Fantastic with Professor Michio Kaku. On Science Fantastic, we profile some of the most amazing developments in science. And we had a call that came in just before the break, and that is explain the double slit experiment. Well, the double slit experiment simply says that one electron, that is a particle, can go through two holes simultaneously, creating an interference pattern on the other side as if the electron were a wave. Now at this point, your brain starts to explode because this means that a particle is not really a dot like Einstein thought, that a particle can go through two holes at the same time. In other words, there is uncertainty with regards to the position of the electron. And this goes to the uncertainty principle, which is the foundation of all of modern electronics. Why do laser beams exist? Why do transistors exist? Why can you hear the sound of my voice going through the ether? It's because of relativity and the quantum theory. So how do we resolve this question? Well, one theory, which is rather unorthodox, but is gradually being accepted by most Nobel Prize winners, that is, my friends, they say that the universe splits in half. This is called the many worlds theory. The universe splits in half, such that in one universe, the electron went through one hole. In another universe, the electron went through another hole, because, of course, one electron cannot go through two holes simultaneously. That's one way to resolve the question. This means that perhaps the universe has parallel universes. Perhaps there's an infinite number of these parallel universes splitting off from each other each time an electron has to go through a hole or each time a measurement is made. Now, Einstein, of course, hated this idea, but hey, what can I say? Einstein was wrong on the question of quantum mechanics. Quantum mechanics is at the foundation of all of modern electronics, all of lasers, all the wonders of modern technology. Why are they so wondrous? They violate common sense. Isaac Newton would go crazy looking at transistors and lasers because Isaac Newton would say that the electron is a point particle. Period. End of story. Move on. No, the electron is not just a point particle. This point particle can split universes. This is called the many worlds theory, and it is the leading theory in quantum mechanics today. Now, just to be fair, there are other theories. The Copenhagen interpretation, you can go to any modern library and have your brains blown out trying to read all the literature on this. But hey, what can I say? We physicists have to confront the fact that the electron, in some sense, can be two places at the same time. And the way to resolve it is if the universe itself splits in half. Okay, well, let's move right along to the next listener phone call.
Hi, this is Mike McGee from Duluth, Minnesota. And my question is, how have human beings affected the 100,000-year ice age cycles? And has global warming actually postponed the next inevitable glacial maximum? Thank you.
Well, you ask a very hot question. First of all, what is the ice age cycle? Ice ages do not occur regularly, like on time. However, ice ages are separated by hundreds of thousands to millions of years. And we think it corresponds to the slight wobbling of the Earth's axis. A very slight wobbling of the Earth's axis can build up over hundreds of thousands of years to change the temperature on the planet Earth. And then the question is, what is the link between that and the next ice age? Well, we'll answer that question after the break. Welcome back to Science Fantastic with Professor Michio Kaku. It's open mic in this hour. Well, before the break, we had a question about ice ages. Yes, ice ages do come roughly periodically, every few 100,000 to a few million years. Right now, we are between ice ages. 10,000 years ago, we were under a half a mile of ice in North America. In another 10 to 20,000 years, we'll have a repeat of that. So right now, we're in what is called an interglacial period. Now, what does that have to do with global warming? Well, not much, because, of course, we're talking about the Earth itself with cycle times of hundreds of thousands of years. Now, if you take a look at the fact that the Earth has been heating up since the end of the last ice age, yes, the Earth has been warming up slowly and gradually. However, within the last 50 to 100 years, there's been a dramatic spike, a dramatic increase in carbon dioxide, and also with regards to the temperature of the Earth. Now, the fact that the Earth is warming up and it has accelerated is not disputed by hardly anyone, because we see that in the satellite data. We see that in all the ways that we can measure temperature on the planet Earth. Where people would differ is where this comes from. Now, again, can this delay the coming of the ice age? No. We're talking about a small spike. We're talking about, when you talk about ice ages, cycles going back tens of thousands to hundreds of thousands of years. So the warming of the Earth, as far as we can tell, will not affect the coming of the next ice age in 10,000 to 20,000 years from now. However, I should point out that with 95% confidence, most scientists looking at their computer programs would say that the recent spike in temperature is not part of the global warming cycle, that is man-made. But that statement is a statement with only 95% confidence. Okay, well, let's move right along to the next listener phone call.
My name is Ricardo. I'm calling from Detroit. What's the point in going to Mars if a long time ago wiped out all living things? I don't get what the big rush to go to Mars would be. Thank you.
Well, you ask a very important question, because right now NASA is planning to go to Mars sometime after 2030. And as I mentioned, Elon Musk of SpaceX wants to do that even quicker by 2024. What's the rush? Well, to be very honest, there's no reason for a rush at all. We had the rush during the 60s to go to the moon because, of course, there was superpower rivalry between the old Soviet Union and the US of A. And we spent roughly 5% of our gross domestic output on the moon program. Now, think about that for a moment. 5% of the entire industrial activity of the United States of America went into the space program. Then, of course, once we went to the moon and came back, we lost interest, and then it fell down below 1%. NASA's budget today is roughly less than 1%, which is probably normal for a science budget of NASA. What's the rush today? Well, if you think about it, the rush is between billionaires and NASA, Elon Musk of SpaceX and Tesla Motors, Jeff Bezos of Amazon, and of course NASA and Boeing Aircraft. Boeing is the creator of their SLS booster rocket for NASA. Now, I once interviewed Carl Sagan, the late Carl Sagan. I asked him that question: what's the rush going into outer space? And he said, well, there's no rush per se, but in the long term, we have to do it. Because in the long term, life on Earth will be extinguished. Either we'll have giant meteor impacts, like what knocked out the dinosaurs, gigantic volcanic explosions and eruptions, or another ice age, or perhaps the ending of the Earth itself as the Earth goes back into the sun 5 billion years from now. So Carl Sagan said, let's be a two-planet, a multi-planet species, because it's an insurance policy. Not that there's a race to go to Mars, but it's an insurance policy, because one day we may have no choice. Welcome back to Science Fantastic with Professor Michio Kaku. Let's move right along to the next listener phone call.
This is Big Al from Chattanooga, Tennessee. And my question is, what's actually happening physically that causes a black hole know to have actual gravitational pull? Thank you.
Well, you ask a question that has bedeviled scientists going even before Isaac Newton. What creates gravity and gravitational attraction? Well, Newton didn't know. He just postulated the fact that objects attract other objects by gravitational pull. Okay, he had no idea as to why, because usually objects move because they're pushed, not because they're pulled. Well, along comes Einstein, who says, I know the answer. Gravity doesn't pull, space pushes. And that summarizes Einstein's theory in one phrase. You see, why are you sitting in your chair today? You're sitting in your chair not because gravity is pulling you to the ground. It's because the Earth warps the space around you, and the warped space pushes you into the chair. That's why you're sitting in your chair right now. Gravity does not pull because there is no such thing as gravitational pull. It's an optical illusion. Einstein says that the Earth warps the space around you and pushes you down. And then you can ask yet another question, and why is that? Like a black hole. A black hole would have objects being attracted to it. Why is it? Well, at that point, Einstein's equations don't tell us. Einstein simply says that if you have mass, if you have energy, if you have a black hole, then it will create a warping according to his equations. Why? We don't know. Okay, it's just the way it is. It's postulated in Einstein's equations. But once you postulate that, it works fine. It satisfies all the data. That's why we give Nobel Prizes now to people who can verify Einstein's predictions about black holes. But why does gravity create this pull? Well, we don't know. It's just postulated by Einstein's theory. And once you postulate Einstein's theory, you can mathematically calculate with very great accuracy the motion of particles as they enter a black hole. Okay, well, let's move right along to the next listener phone call.
Hi, my name is Ron, and I'm calling from Gardner, Massachusetts. I'm listening to WGAW 1340 AM radio. My question is about Martian gravity. I read some material about the International Space Station and how there's bone loss and other bad effects of low gravity. Well, is Martian gravity high enough? I think it's about one-third Earth gravity. Is it high enough to prevent that bone loss and other serious effects of zero gravity? Thank you.
Well, the short answer is no. First of all, you're absolutely right. Astronauts in weightlessness on the space station basically lose calcium, phosphorus, many vital elements of the muscles and the bone. In fact, Commander Polyakov, the Russian astronaut who set the world's record for being in outer space for over a year, when he came back down to the planet Earth, there's a motion picture of him getting out of his space capsule. He crawled like a worm. He crawled like a worm. There was so much atrophy in his muscles and bone that he could not even come out of his own space capsule and walk. So our astronauts suffer bone loss, some of it permanent, by the way. I repeat, some of it is permanent bone loss. So we have to have our astronauts exercise all the time. We have treadmills in outer space with a rubber band so that you have tension on that treadmill. And you have to exercise several hours of the day because you will have bone loss. Now, as you correctly pointed out, Mars has a weaker gravity than the Earth, roughly 40% the gravitational pull of the planet Earth. They will suffer bone loss, not as much as out on the space station where there is no gravitational pull at all. However, yes, there will be bone loss even on Mars, because of the fact that Mars has a lower gravity. In other words, our body is fine-tuned to live on the Earth. If the Earth's gravity were a little bit stronger or a little bit weaker, our architecture of our body would not be adequate to live in that environment and flourish. That's why we have to do things like exercise. That's why we have to do things like, well, eventually maybe even genetic engineering, so that we can survive on planets with different gravitational pull. One solution to the problem is to spin our spacecraft like a ball on a string. That's very expensive, but yeah, you could create artificial gravity and quote unquote solve the problem of weightlessness, but it would add a tremendous cost to our space program. Okay, well, let's move right along to the next listener phone call.
And my question is about dark energy. If dark energy, as we know, is the continual expansion and acceleration of the expansion of the universe, how do we know it's this mysterious energy and not the gravitational attraction from some huge amount of mass beyond our range of detection outside of the known universe, and in reality, that instead of everything expanding, that everything within our known universe is actually falling and accelerating towards this unknown mass that's beyond our detection, and it's really just gravity causing that. Thank you.
Well, you ask an interesting question. Einstein tells us that the universe is expanding, and expanding very uniformly, by the way. But then you ask another question. Maybe it's an optical illusion. Maybe it's not expanding at all, but going toward an attractor. Well, that would be non-uniform. Now, it turns out there is a great attractor. It turns out our galaxy is moving toward an object asymmetrically called the great attractor. But that's not the universe itself. The universe itself is uniformly expanding, as we see in the microwave background radiation. That's why we don't believe that the attractor can have enough uniform force to make the universe appear to expand. So in other words, the universe is expanding.
Science Fantastic with Professor Michio Kaku.
This is Science Fantastic with Professor Michio Kaku. On Science Fantastic, we profile the amazing, jaw-dropping scientific discoveries which are revolutionizing our world and touching our lives. And in this hour, once again, we're going to throw the lines open. That's right, it's open mic on Science Fantastic. Okay, well, without further ado, let's take the first listener phone call.
Can solar energy be used to produce hydrogen profitably so that it may be stored and used by Japanese car engines which are supposed to be built? Would that be another way to store solar energy? Thank you.
Well, you're asking a question which in the next few years will be answered, and it could be a game changer. Some people think that the ultimate car, the car where waste is nothing but water so pure you can drink it, and it uses electricity, and the energy source is hydrogen. These are called fuel cell cars, and fuel cells were pioneered by NASA. Our space probes in deep space use hydrogen fuel cells to create energy. And so, therefore, if NASA can do it, why can't we do it on the planet Earth? Well, the problem has always been cost. You see, a hydrogen car, in some sense, is the ultimate car. Remember in elementary school, we learned that if you take oxygen and hydrogen, H and O, and you put H and O together, what do you get? Bingo, H2O, water. That's the secret of the fuel cell. By combining oxygen and hydrogen with a spark, you can release even more energy, and the waste product of this combustion is water. Water so pure you can drink it. And Toyota is now coming out with the first mass-produced, commercially available fuel cell car. And then you may say to yourself, well, if it's so great, what are the drawbacks? Well, there are some potential drawbacks. First of all, remember when Henry Ford first came out with the automobile? Many people thought that, hey, we're not going to have automobiles everywhere because who can imagine gasoline stations on every block? That's ridiculous, people said 100 years ago. Gasoline stations every block? We won't tolerate that. And gasoline burns and explodes and it's combustible. Who wants to have a car accident where people are burned alive? So people thought that the automobile would never become mass-produced. Well, all those predictions were wrong. We live with car accidents. People get burned alive all the time in car accidents, and we do have gas stations on every block. Well, why not have a hydrogen car? Some people say that, well, hydrogen has problems. First of all, you would have to have hydrogen refueling stations every block, and that's not going to happen. And next, hydrogen is explosive. Remember the Hindenburg, which blew up a gigantic blimp which blew up, it had hydrogen inside. Well, hydrogen is volatile because it has stored energy just like gasoline. And some people think that maybe one day we will have hydrogen refueling stations on every block. Well, the caller said maybe the way to get energy for the hydrogen is solar energy. So here's how it would work. Solar energy is energy from the sun. With solar cells, we can convert that to electricity. With electricity, we can store it in a battery. And with a battery, we have an energy source that can thereby get energy from oxygen and hydrogen. We can separate out oxygen and hydrogen from water. So seawater is the basic fuel for a hydrogen car. So electricity from solar allows you to separate H2O into H and O. Then you put H and O in your car, combine them in the car to produce energy, and you can literally drink the waste product from the combustion process. And so is it a pie in the sky? No. What it takes is some large corporation like Toyota to jumpstart the technology. So all the pieces are slowly coming together. Remember, you're not going to have a fuel cell car immediately, but Toyota is now beginning the process of marketing the first generation of hydrogen cars. Now realize that there is another problem, and that is, where does hydrogen come from today? Hydrogen comes from today from electric utilities which burn coal, and coal, of course, is polluting. So one drawback is you have to burn coal to produce electricity to therefore create the hydrogen which can be burned cleanly in your car. Eventually, we want to eliminate the coal-fired plant, and that's where solar comes in. And so the answer to the question of the caller is that, yes, this could be the future. Is it now? No. But in the coming years, we hope to create solar cells that are competitive with coal so that we can realize the dream of energizing the hydrogen car.
This is Science Fantastic.
Welcome back to Science Fantastic with Professor Michio Kaku. This hour is your hour. This is the time when you can get to the airwaves and talk back to national radio. Why do you have to watch TV or listen to radio and have a one-way street? Why not be part of the dialogue? Why not be part of the discussion? Okay, well, moving right along, let's take the next listener phone call.
We have ever tried to send anything into a black hole to see if it would come out somewhere else or if it would send data back to us to let us know if black holes can be used in our advantage. Thank you.
Well, you ask a question that is at the cutting edge of physics research, and we have an active group now looking at the black hole which is raging in the center of the Milky Way galaxy. We live in the Milky Way galaxy. That's our home galaxy. It consists of about 100 billion stars, and dead center in the Milky Way galaxy, there's a raging black hole. It's a monster of a black hole. It weighs about 2 to 3 million times the mass of our sun, and we can actually see it having lunch. That's right. It gobbles up entire star systems and gobbles up a tremendous amount of gas and emits a tremendous amount of energy as a consequence. So your question is, well, what happens if you throw something into a raging black hole? Well, first of all, if you want to see this black hole, tonight, if it's not too cloudy, go outside and look in the direction of the constellation Sagittarius. And there's a part of Sagittarius called Sagittarius A, and that is where the center of the Milky Way galaxy is. Now, by rights, there should be a gigantic fireball in the direction of Sagittarius, which comes out every night, marking the center of our galaxy. Unfortunately, our galaxy is quite cloudy, quite dusty, I mean. In fact, we came out of cosmic dust, or the Earth itself is made out of the dust in the galaxy. But because there's so much dust in the galaxy, we cannot see the raging galactic nuclei, and we certainly cannot see the black hole at the very center of the Milky Way. And so, since the center of the Milky Way is many, many light years away, we do not have the capability of sending a rocket through the black hole. Now, as the listener said, there is a theory, taken rather seriously, that at the other end of the black hole, there could be a white hole on the other side of the universe. So if you fall into a black hole, perhaps you're blown out the other end of a white hole. And so perhaps falling into a black hole is not death after all. Well, that's a theory. We don't know for sure. However, there seems to be some mathematical backing for this theory. If you take Einstein's equations, which predict black holes, and you find that, yes, black holes, if they're stationary, the gravity is infinite at the center, and you die when you go into a black hole. But, and here's the caveat, if the black hole is rotating like a spinning top, the black hole does not collapse to a dot, it collapses to a ring, a rotating ring. Centrifugal force prevents the ring from collapsing. And if you fall through the ring, through the north pole of the ring, you do not die. Gravity is not infinite at the very center of the ring. And in fact, you can fall right through. So if you have enough positive energy, you can actually fall right through a black hole. Perhaps there's a white hole at the other end. Well, then the question is, how stable are these black holes? To stabilize it, you have to keep the ring open. To keep the ring open and not have it close, you have to have something called negative energy, which is quite exotic, very difficult to manufacture. So some people say, well, why can't we build the black hole machine in our basement and use that to travel to the stars, just like they do in science fiction movies? Well, if you do the calculation, it turns out that you need positive energy, like a black hole, on a scale of stars. And so we are nowhere near being able to harness the power of a star. And then you need negative energy to keep it open. So once again, you need positive energy to create a tunnel through space-time, and negative energy to keep the tunnel open. So this is not for us. Let's face it, we can barely manipulate trains and planes on the Earth. We cannot manipulate the Earth itself, and we certainly cannot manipulate the sun, and we certainly cannot manipulate energy on the scale of a black hole. But it's nice to think about. Perhaps aliens in outer space have already done this. If you saw the movie Interstellar with Matthew McConaughey, they actually realized this scenario. They actually traveled through this wormhole to a distant part of the galaxy. Then the question is, who built the wormhole? At the very end of the movie, they hint that the people who built the wormhole were, well, us. We built the wormhole. That is, our descendants. Our descendants, many generations into the future, built the wormhole, which allowed them to communicate with the past, which is us. And so in some sense, our descendants created the wormhole, which allowed Matthew McConaughey to go into a new sector of the galaxy to reseed the human race. Well, is it science fiction? Certainly it's science fiction. But is it rooted in fact? Well, it is rooted in theory. Einstein's theory does allow for the possibility that you can fly right through a wormhole and wind up on the other side of forever. Okay, well, moving right along, let's take the next listener phone call.
What do you think about the mining of graphite in America for the electric car batteries?
Well, one of the hottest things now in the energy market is batteries. And then the question is, how would you mine the material? How would you make a cheaper battery? Lithium-ion batteries seem to be the cheapest and most efficient form of batteries right now. Well, let's take a look at this question historically. Henry Ford and Thomas Edison were rivals, but they were also friends. They would actually vacation together sometimes, and they had a friendly bet. The bet was what would propel the cars of the future. Henry Ford, of course, bet on gasoline, while Thomas Edison bet on the electric battery. Well, who won the bet? Ford won the bet because electric batteries have always been the bottleneck in our quest for energy. Batteries do not store much energy. They're not that reliable. They cannot be used both for fast pickup as well as long-term driving. And so that's the reason why we have gasoline in our cars and not battery-powered cars. However, perhaps Thomas Edison will eventually have his revenge because the cost of batteries is going down. It's the hottest thing now in the energy market. They're becoming cheaper, more efficient, and costs are dropping at the rate of about 7% a year, which is enormous. In fact, in the next few years, we expect the cost of batteries to go down by a factor of about 50%. And that means that perhaps batteries will rival gasoline as the source of energy. Not yet, but in the coming years, we could see it happen. Now, some billionaire is going to make a lot of money producing this battery. And some people say that Elon Musk could be that billionaire. Okay, well, let's take a short commercial break. Welcome back to Science Fantastic with Professor Michio Kaku. The lines are open. You're not going to get a busy signal. You can get right to us. You can record a comment or question, and perhaps your thoughts and your thinking will be on Science Fantastic and National Radio. It's open mic, so any and all questions are fair game in this hour. Okay, well, let's take the next listener phone call.
Yes, Professor. My thesis is to deal with sound resonance and molecular resonance, and if there is any correlation between those two. Did see some programming on possibilities that large objects were able to be moved by sound waves. I'm looking a little bit closer at home, the possibility of cleaning water via sound waves, desalination and the like, and I'd like your input on that. Thank you, sir.
Okay, well, first of all, you're absolutely right. Sound waves can carry an enormous amount of energy. In fact, the Pentagon even once considered using sound waves as a weapon by shooting sound at an enemy vehicle. And you also mentioned, well, the possibility of sound waves to clean water. Well, sound has a number of applications. However, the leading technology for desalination is to use heat. So let me back up a bit. In California right now, this is one of the hottest topics. That is, California is suffering from a massive drought, a drought that's lasted several years, prompting counties to say that perhaps the solution to this problem is desalination. That is, boiling water so that water evaporates. You collect the evaporated water and recondense it, and you get pure water, leaving behind brine or very thickly concentrated salt water. And so it's a very energy-intensive process. It's not cheap at all. Sometimes I lecture in the Middle East, and when I travel through Saudi Arabia or Dubai, you see these gigantic fountains in the middle of the desert. In fact, in Dubai, they even have an area where you can ski on snow in the middle of a desert. You can actually do that because of the desalination program. They have massive desalination plants because they have lots of energy. So in some sense, you're exchanging energy for water. Energy is used to evaporate or boil water. What's left is salt water, which you dispose of, and the clean water then is condensed and gives you drinkable water. And then the question is, can sound waves do this? Well, I have my doubts. I have my doubts whether or not sound waves has the capability of separating salt from water, but hey, we'll see. In fact, now that California is facing this crisis, There are going to be a lot of inventors, a lot of entrepreneurs who are going to be looking at all sorts of schemes to begin the process of desalinization. And so, in fact, some people think that in the future we could have water wars. For example, look at the Middle East. Also look at global warming and the changing of weather patterns. Some people think that with the changing of the weather, certain areas will become more arid, other areas will become drenched with water, and perhaps that'll be a stimulus for desalinization. For example, again, let's take a look at California. Why does California have this big debate about desalinization? Well, because of this drought. Well, why is there a drought? Because there's an 800-pound gorilla in the living room. The 800-pound gorilla is a high-pressure area that is sitting on California. Look at the weather maps. You usually see this big H right over Los Angeles. That H is a high-pressure area, and what it does is it deflects. It deflects cold air from the Arctic, pushes it over to the side in Canada, where it hits the Northeast. And so in some sense, the heavy rain, the flooding, which we in the Northeast are experiencing, I'm in New York right now, the heavy rains that we're getting, in some sense, should have fallen on California. But they didn't, because this high-pressure area pushed this cold air into New York and the Northeast, leaving a drought in California. Now, I warn people that there's a problem here. And that is Australia had the same problem. For 7 years they had a drought. They built massive desalinization plants. And then what happened was the drought ended. The drought ended. And they're left with billion-dollar desalinization plants that are underutilized. And so that's a cautionary tale. But, you know, even though I doubt that sound waves can be used for desalinization, I think that a lot of entrepreneurs are going to be looking at a lot of unorthodox methods to separate out salt from seawater because of the enormous potential market in California and the American Southwest. Welcome back to Science Fantastic with Professor Michio Kaku. It's open mic in this hour. Okay, well, moving right along, let's take the next listener phone call.
Got a question. Since you can use flame to propel a spacecraft, why couldn't you use light to propel a spacecraft? You'd still be forcing it away.
Well, you're absolutely right. In fact, some physicists have even looked at science fiction schemes of building a starship. These are called photonic starships that use light beams, specifically laser beams, in order to propel themselves. One theory is, why not build a gigantic sail? A gigantic sail that is hundreds of miles across in outer space, where you can build these things, and then put banks of laser beams on the moon. These laser batteries would then fire tremendous amounts of energy at that sail, thereby inflating the sail and pushing the sail towards, let's say, Alpha Centauri. When you do the mathematics, of course, you have to have a tremendous number of lasers on the moon, but it is conceivable. It's conceivable that you might reach maybe half the speed of light riding on a sail. Another idea is, why not scrap the engine of a rocket and put a laser beam there, a gigantic laser beam, such that on one side of the rocket it shoots out a laser beam. On the other side of the rocket, you're propelled by Newton's third law of motion. For every action, there's an equal and opposite reaction. And thereby you're literally riding on a light beam. Is this possible? And the answer is also yes. Now, of course, we don't expect to build these things anytime soon, but perhaps in the next century, solar sails, laser rockets, photonic rockets will be looked at very seriously. In fact, the Planetary Society recently launched a satellite into orbit that has a small sail. And so either you sail on a light beam, perhaps from the sun, or a laser beam on the moon, or perhaps you use the laser beam itself as a rocket. Now, you may say to yourself, well, isn't this a slow process? Well, the answer is yes. We are used to seeing booster rockets flaming away so you reach maximum velocity in just a few minutes. That's not the way these solar cells work. When you turn on the solar cell, nothing happens because you're riding on light, and light has very little mass. Therefore, it takes, well, maybe a year or so to slowly build up the velocity necessary to fling yourself toward the stars. So this is a technology not for this century. It's a technology for the next century. And who knows? Maybe one day it could take us to the stars. Okay, well, moving right along, let's take the next listener phone call.
My question is about the force that comes from a fire, and is that why the rain is diverted away from forest fires, from the energy from the fire?
Well, yes and no. If you have a massive fire, it generates a tremendous amount of heat. Heat rises, and therefore when rain falls, it encounters this blanket of hot air, which is rising, and therefore can deflect it. And so it is the heat from the fire which causes the deflection, not necessarily the fire itself. And then another question is, well, what is fire? Fire is nothing but hot gas hot enough so that it begins to glow. Okay, well, let's take a short commercial break. Welcome back to Science Fantastic with Professor Michio Kaku. It's open mic in this hour. So, moving right along, let's take the next listener phone call.
Hi, Dr. Kaku. I actually had a question about tidal forces and Roche's limit, and you were talking about how the moon is actually leaving our planet away from Roche's limit at a couple of inches per year, and I was just wondering, what type of effect does that actually have on our tides and our tidal forces on planet Earth? And do you think that actually has any sort of effect on climate changes and weather changes as far as what's going on the planet? Thank you very much.
Okay, well, first of all, I don't think that climate change is going to be affected that much by tides, but let's say a few things about tides. Of course, we all know that when the moon is more or less overhead and the sun is in a certain position, water in the oceans begins to rise. And the ancient mariners had to know when the tides came in and out, or else they didn't eat. They couldn't launch their boats on low tide. And so it was life and death that people categorize all the motions of the tides. So where do the tides come from? It comes from the pull of the moon. The moon tugs on the earth, and therefore the water rises, believe it or not, because of the gravitational pull of the moon and the sun. But you see, the earth also acts on the moon. And so even though the tides are not very great, you don't see rock go moving up and down, the Earth does exert tidal forces on the moon. And that's why, as you pointed out, the moon is leaving us. The moon is leaving us at a few inches per year. And if you run the videotape backwards and try to calculate at what point the moon came out of the Earth, you get roughly the correct answer. Roughly 4 billion years ago, that's when we think the moon was blown out of the Earth. And so does it affect climate change? Probably not. In the sense that we think that climate change is driven by natural cycles as well as human intervention, that is the burning of fossil fuels. And so we don't think that tidal forces will affect climate change. However, tidal forces have shaped the Earth and have shaped the moon. Also, have you ever noticed that you've never seen the backside of the moon? Think about it for a moment. Think of the moon right now. Think of the moon. It's the same double moon. You've always seen the same moon. You have never seen the backside of the moon unless you've seen pictures from the space program. And why is that? Because of tidal forces, the moon is synchronized with the Earth. And the synchronization process is also a consequence of tidal forces, all of which comes out of Newton's theory of gravity. Given Newton's theory of gravity, you can actually predict all the motions of the tides. Now, what happens if the moon comes too close to the Earth? Well, our moon is not coming too close to the Earth, but if it did, if our moon got too close to the Earth, it would be ripped apart by tidal forces, and that's where we think the rings of Saturn come from. The rings of Saturn, we're not sure, but the rings of Saturn probably come from a satellite that got too close to Saturn, and tidal forces ripped that moon apart, giving us a beautiful ring. In fact, according to Newton's laws of gravity, you can calculate the distance at which moons are ripped apart. And bingo, that's exactly where we find the rings of Saturn. That's called Roche's limit. Roche's limit is the radius at which rings form because tides will rip apart a moon. And sure enough, the rings of Saturn lie exactly at Roche's limit. So tides not only are life and death for fishermen, tides not only synchronize the moon, pushing the moon away from us every year, but the moon is also very much involved with the creation of the rings of Saturn. Okay, well, moving right along, let's take the next listener phone call.
Dr. Kaku, this is George in Portland, Oregon, listening to you on AM 970. My question for you is, do you think in the future it will be possible to create solar-powered space engines?
Yeah, that's very similar to the phone call that we had before. These are called solar cells, and we think that solar power may inflate a sail and take us into outer space. However, sunlight cannot energize a starship way, way in deep space because sunlight is too feeble. At that point, we have to turn on our laser beams. So, in other words, to get out of the solar system, we may have a huge sail, a sail maybe even thousands of miles across, that can capture the pressure of sunlight to push us out of the solar system, but then to sustain it, to go all the way to the stars, we may have to turn on our laser beams or have a laser beam on the moon energize our sail from that distance. Then the other question is, if you have a solar sail, how do you stop? Well, that's a problem, right? The answer is, halfway to the nearest stars, we have to turn around and then start to use the energy of the destination star as a brake. And then you whip around the star and use the slingshot effect to come back. And so tacking with a solar cell is a lot more difficult than tacking with a traditional sailboat. Okay, well,